All right, master students, let's just proceed from where we left. Uh, uh, I was mentioning something about the Arrhenius equation, and and it's something which came up from an observation of this scientist who was trying uh, to plot some experimental data on having a rate constant k. Now, I need to emphasize this one from the word go, because there are two letters. No, there is that letter. Um, uh, it's used to show two different variables, and both are very important in chemistry. So this one here is the small k. Small k uh, is a reference to the rate constant. Rate constant, you're going to use small k. And then there is the capital K, which implies the equilibrium constant, capital K. Please note this. We are not talking about the equilibrium constant, capital K. Are we noting this? We're not talking about the equilibrium constant, which is given by the ratio between the concentration of the products over the reactants. In this case, you're talking about the rate constant, which is the proportionality constant. When you remove the proportionality constant between the rate and the concentration, you get the rate constant. That is what you're talking about, the rate constant, yeah? This one is vanishing, yeah? So you're talking about the small k, yeah? The rate constant. So that in this case, you've got one reaction, there is a rate constant. No, not one reaction. You've got the same reaction, but you are varying the temperature. As you vary the temperature, then the rate constant is going to change. Yeah, the rate constant is not going to be the same as at 20 degrees, at 40 degrees, 50 degrees, and the rest. Yeah, so the rate constant will change with the temperature. Is that okay? And sometimes you're going to see, if you're just going to probably it's not been it doesn't apply to all the temperature, but you're going to see by just doubling the temperature, you may see the rate constant can increase 10 times. Yeah, that's in general, that's the average. But in certain reactions involving strong covalent bonds, it may not be the situation. But in general, by just doubling the temperature, you can increase the rate constant by 10 times. Yeah, okay. So that in this case, here is a plot of here is the plot of the rate constant, and here is the plot of the temperature. So what this scientist did, called Arrhenius, said that, hey, what if I was to get the natural log of the rate constant, and then I plot against the same temperature? Then he got an interesting result, and that interesting result is a straight curve going down. So there was the log base e, not natural, not the log base 10, log base e of the rate constant plotted against the temperature. So there was a negative plot with uh, so there is an intercept which is being given as an A, and then I was trying to now come up with the what to interpret that data, and then out of all that, he came up with this equation here, that the rate constant is equals to something called a pre-exponential factor called just gave a letter A, and then there's the e to power, and then he realized that that the information here is giving the slope as the activation energy over the gas constant. So that in this case, the only thing which is the unknown, is the activation energy. Can you see that? So there is this equation here: k is equals to, the small k is equals to pre-exponential factor A multiplied by the e to power ea over rt, where where T is the temperature in Kelvin. So if you've got this equation, to try to show you how you're going to get to this plot here, um, so just put a natural log before this equation. So this will become natural log of k is equals to natural log of everything in there. And once again, there's some books which I'm going to give you a link, which are going to show you if you've got this logarithm, how you can be able to expand it. But if you've got something like this one, it's just like if you're going to expand, it's similar to an addition. This will become log base natural log of a plus natural log of this one, and log base something of something to that one, it becomes that value. So all of this becomes natural log of a minus, because this is minus so this becomes minus ea over r, because log base e of e becomes what, 1, yeah, becomes 1. So so um uh, so this is what you are going to get here. Natural log is equals to natural log a minus ea over r. So what you're going to see is that if you're going to be plotting the natural log versus the temperature, then the gradient will become ea over r, and then the intercept will be natural log of a. So from the natural log of a at that intercept, then you can actually determine that the exponential factor, which is going to be a constant for the reaction. Yeah. Now, what has been seen is that you really don't need to determine that uh, pre-exponential factor a. So if you're going to take two reactions, just take two reactions in which you say I'm determining probably a reaction at maybe uh, 20 degrees, another one at 25 degrees. So you're going to convert those temperatures to the Kelvin, and then find out the rate constant at 20 degrees and the rate constant at 25 degrees. Keep those values. So if the rate constant at probably a lower temperature, it's going to be given by this. So the only thing which is going to be varying here will be rate constant 1 and also temperature 1. So this equation I'm going to call equation 1. Can you see why? And then at temperature 2, I'll have a second rate constant, and then there will be temperature 2. Oh, sorry. So let me put this one equation 2 here. So I want to subtract equation 1 from equation 2, yeah? So there will be ln k2 minus ln k1 is equals to, it will be the first thing, this thing on the right. No, it will be the one or the lower one, and then I subtract. It will be equation 2 minus equation 1. So if I'm going to open up, I'm going to see, in this case, there will be a positive ln1 and so it will be a negative. So those things are going to cancel. And then I'm going to get minus ea over 1 rt2 plus ea over 1 over rt1. So if you're just going to rearrange, I'm going to have this plus, I put it outside. I'm going to put it, first of all, ea over 1. So I'm going to get ea over r, 1 over t1 minus 1 over t2. Yeah. So in this case, you can be able to determine the activation energy of a reaction if you know the two rate constants and the temperatures at which they are being carried out. So just given a simple example here in which there are these different temperatures. Please note this. The temperatures are given in Celsius. Like this is 477, 523, 577, and 623 Celsius. And then these are the rate constant in per second. So 1.8. Actually, the thing was given in decimal, but I converted to that exponential form, so that this standard format, so that would actually be seen well from yeah, from that side here. So So based on this data, you come up with this data here, like this 477. What you're going to see is that this 477, uh, you add 273 Kelvin to get what? I think it's 750 Kelvin, and then you take the reciprocal of that, then you're going to get a figure of 0.00133 something. So if you're going to get K times 10 to the power minus 6, then you're going to get these figures, yeah? You're going to do the same thing for those, yeah? And then you're simply going to take the natural log of uh, of the rate constants. Uh, if such a situation is going to happen in an exam, like in a CAT or an exam, you're going to be given a graph paper. So that in this case, you're going to plot the natural log of excuse me. So there will be the natural log on the y-axis, and in this other case, there will be the temperature. Yeah. Uh, okay. So in trying to if you're going to plot that, and you're going to get a what? You're going to get a slope of 3.27 times 10 to the power 4, and in putting to this one, you're going to get an activation energy of um, you're going to get an activation energy of sorry uh, wait a minute, this is supposed to be 1 over t. Sorry, it's going to be 1 over t. I'm really sorry for that. Yeah, I think hope you can really go back to that one. You're going to see that the the straight line is actually being given by the relationship between what? uh, okay, it's going to be given as a relationship between the. Uh, let me get it on this equation here. Relationship between the natural log of k and the reciprocal of the t. Yeah? Are you clear on that? So that in this case, I'm going to get, so this one will be, in this case, the gradient will be negative minus EA over R, and then the x-axis is going to be 1 over t. I'm sorry for that. And then the y-axis it will be log base E of the natural log. I'm really sorry for that. So this will be what? 1 over t as opposed to plotting t. Please note that. So the plot will be what? Natural log or log base E of the rate constant, small k here, and then here it will be 1 over the reciprocal of the temperature. So that in this case, if this is the temperature in Celsius, I'm going to add 273 to get the temperature in Kelvin, and then I determine the reciprocal, and then I get a figure like for this one is if I take that reciprocal, I'm going to get 1.25 times 10 to the power minus 3. Yeah. So if you're going to plot there, then the slope will be, in this case, it will be minus 3.27 times 10 to power 4. Yeah. So if you're going now to do what? To do what? Okay, let me get it on that one. EA. I'm getting that that slope. So I'm going to multiply. Okay, let me get it correctly. What? So that is the slope multiplied by the R. That's going to give you the activation energy. Yeah? Okay, good. So so the EA it will be given by the slope which you are going to get multiplied by the R. That's going to give you the activation energy. Yeah? I want to see whether I hope I've not moved quickly, so that in this case you can see that from plotting the figures you can be able to get the activation energy of a reaction on that. Okay, so you're going to get a negative slope, so that in this case there will be the gradient there, and then I'm going to multiply by R to get the the negative R to get the positive activation energy. Yeah? Okay, good. So I think that's the much I'll talk about the Arrhenius equation, and I think uh, from the tutorial questions and the past papers, you can be able to look at the at how the solved questions dealing with the Arrhenius equation, how they've been tackled with. So I hope this small talk on the Arrhenius equation has really opened up your understanding on how to determine the activation energy from the experimental data in which you know the rate constant. Okay, so I'm just going to stop there, and then I think we'll proceed shortly with other topics. Okay, good.